Guys, we are back with another problem, and today's problem is a two-dimensional matrix problem. It's one of the most fundamental problems which you should be having an idea before you solve any problems on DP series is how to deal with a 2D matrix and their row and column transformations. Okay, so welcome back. So if you see in today's problem statement, we will be given a matrix, say 0, 0, 0. Okay, so let me just quickly draw the matrix. So first has 4 zeros. 1, 2, 3, 4 zeros, 1, 0, 0, 1, then 0, 1, 1, 0, 0, 1, 1, 0. So now the question is we have to count the total number of possible ones which is surrounding a particular zero. So the criteria is like this, that in how many ways zeros can be surrounded by ones. Okay, so if there is a zero, you can see it can have a 1 on the left side, 0 can have a 1 on the right side, and 0 can have a 1 on the downside as well. Okay, so if you check the possibility, you have to go to the deepest point. You have to go to the deepest point in all directions. In all directions. So this is the rule of the matrix. So if you have to check, what you have to basically do is, suppose I have to divide this into, say, rows and column. Okay, so this is my columns and these are my rows. So if I see carefully, and if I see for this particular index, so for this particular I can write row 1, row 2, row 3. Okay, and for each rows I have to check the possibility of zeros. So for each row, for the first row, say row 1, what I can see is there is 1, 0, 1, 1 over here, 1, 2, 3. So total number of ones is 1 plus 1 plus 1 plus 1 equals to 4. Now let's check for row number of 2. Okay, so row number 2. If you check in this particular row, there are 2 zeros possible, 2 zeros possible. Okay, and each of these zeros, for each of these zeros can have how many ones surrounding. So let us take, for example, this particular zero. This particular zero has 1, 1 over here, 1, 1 in the deepest node over here, and 1 over here. So we are giving it as 3 plus. Now let's consider this particular zero. For this particular zero, it has similarly 1, 1 over here, here, and here. So it has total of 3. So in this row 2, we are getting a total of 6 such counts. 6 such counts. I can write it over here. Such possible counts. Possible counts. And for this particular zeros, if you see, it has how many ones surrounding it. For this particular zero, it has how many ones surrounding it. Okay, so if I check for the third row, it has 1, 1 over here, 2, 1, 2. So for this zero, there is 1 and 2. For this zero, there is 1 and 2. So I can write for row number of 3, the total number of counts, such counts surrounding ones will be 2 plus 2 equals to 4. Okay, 4. Now what I have to return the total count. So in this case, the total count is 14. How? 10 and 4. Okay, 6, 4 and 4. So you can write it like this: 6 plus 4 plus 4. Okay, so this is what we have to return. So let us go with the code. You can see carefully that we have been given a class solution. Okay, so here we are defining a class. Say we can define a class. Okay, now here the user is giving the two-dimensional matrix, the 2D matrix which we are passing. A 2D matrix has rows and columns, and rows is controlled by the ith index and columns is controlled by the jth index. So matrix n equals to matrix dot length. So what does this basically do? This gives you the entire length of the matrix. This gives you the entire length of the matrix. So say for example, if I'm considering this particular matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can see the like total values, how many values you can have. Okay, what is m? So we have got one n, and what is m? So for m, I can write length of row. So what is my length of the row? Basically, whenever you're denoting matrix in third bracket 0 dot length, it means you are considering the first row, which is R1. You are considering the length of R1. Okay, So over here we can see length of the row. Next, what we are doing, basically we are doing count equals to 0 to check the count, of the particular matrix elements, such elements which I mentioned over here, such possible counts, we have to take the counter as 0. Now I'm traversing through the initial matrix rows, now inner row. So J is nothing but traversing through the inner row. I can say inner row. Okay. Now if matrix of I and J equals to 0, what does that mean? It means that whenever we are encountering a particular element which is 0 or not. So I and J is nothing but index, right? So whenever we are getting a particular matrix, say mat of I J equals to 0. What does that mean? That the element present is 0 or not. Okay. Similarly, we can write it over here. We are checking that whether the element is 0 or not. Okay. This is also done. Now, next part is in the M. What we have to count is whether J plus 1 is less than M, or matrix of I and J plus 1 is equals to 1. So what is J plus 1 less than M? So suppose we are over here. Okay, suppose we are over here, and this is known as I comma J. Okay, I is the rows and J is the column. So 1 2 3. Okay, 1 2 3 4. Okay, so you can see there are particular rows and column to this particular case. Okay, and I'm going to draw a sample matrix in order to understand this. Whenever I'm checking that matrix of I and J plus 1, means I is constant, means my rows is constant, but I'm checking the element in this particular row. Say for example, whenever I is constant, means we are over here, we are placed over here, we are not allowed to go to 2, or we are not allowed to go to 3. That means you can see in all the cases for a given row, we have to only check the right side, right? We have to check the right side, we have to check the bottom side. And how we are going to do, I will let you know. So in this case, you can see J plus 1 is less than M. Okay, that satisfies that condition, that the element present over here has an index which is less than equals to 4. Yes, because obviously the length of the row at particular instance is 4, so it has to be lesser than 4. Now matrix of I and J plus 1. So assuming this is I, this is suppose J. Okay, so the J plus 1 element will be over here, so the adjacent. So J plus 1 is nothing but right adjacent. So this is how you can traverse, right? So we are checking if the element present at the right adjacent is equals to 1. Then we are encountering a 1. That means we are surrounded by 1. So we are increasing the counter by 1. Okay. Now similarly, we are checking J minus 1 lesser than equals to 0. That means suppose we are over here at this point and we have to move to this point. Suppose our element is present at this point and we have to check whether a 1 is present over here or not. Suppose we are over here and we have to check whether a 1 is present over here or not. So that means J minus 1 denotes left adjacent. Okay, we have done with the right and left. Now I minus 1 and J. So basically I minus 1 is nothing but your downmost element. Suppose you are particularly placed over here, you want to check if 1 is present over here or not in your down box. Similarly, I plus 1 is checking whether over here and any element is present over here or on top of it. In both the cases, in all the cases, we are going to increase the counter, and finally we are going to return the counter. It was an easy problem, but you have to be careful while you are indexing. So in case you are I plus 1, that means top, and I minus 1, that means down. Okay, based on that you have to work. So again, we have also checked that J minus 1 is greater than equals to 0. Yes, because J minus 1, suppose you are moving over here. Suppose by moving from shifting, you reach an index 0, 0, which is your starting index. You just can't go back, right? So you have to always be greater than equals to 0 in case of moving towards the left. You can see you have to be greater than in case of moving towards the left. Also, when you are going to the top, you have to be careful that the 0, 0 is there, right? So in either case, whether you are moving across the rows or columns, 0, 0 is the minimum value, and you are returning the count. So you can't just traverse an element which is, say, beyond this. There is no element beyond this, right? So this is your ultimate limit. That's why we are using 0, 0 over here. Similarly, for moving down, we are using the length of the matrix as n. Okay. So these were all the conditions. I have clearly mentioned the conditions, and this is the code. You can execute it and it works. There are 230 test cases it will pass all the test cases. So I hope you like this solution, and we are looking forward to solving more problems. Thank you.